Okay, hello everybody, good morning. Again, hope you are doing well and you are good. So today we are going to talk about the occupancy grid mapping. But before that, if you have any question about previous course and or your topics about the project, you can feel free to ask. So for this course, you don't need to present your project in class. You just need to send me final topic that you are going to work. And if you think that you have any question about your project or about the topic that you're going to choose, you can directly talk to me. It's fine. Okay. No question? Good. So today we are going to talk about the occupancy grid mapping. We already seen how grid mapping is looking like in previous course, a little bit general. We want to see more in detail how we can use the concept of occupancy grid mapping with base filter and how we can update the map construction in our localization algorithm. So whatever the technique that we are using, finally we need to construct the map. And let's dive in how we can work with it. So first of all, we will talk about map in measurement models. Then we will talk about the occupancy grid mapping. Then we will talk about the sensor fusion. And if we have multiple kinds of sensor, what are the general topics to fuse the different kinds of sensors together in order to be able to use them for constructing the map. And we will see general idea of the learning inverse measurement model. We will first formulate what is the inverse measurement model. Then we will see how we can engage learning techniques and algorithms in order to use them to construct the map. So first of all, let's have a look at what was the map. If we talk about the map, we can say we have feature-based maps. That in feature-based maps, our sensor model extracts features of the environment. For example, you have camera, robot camera looks at the environment, and with that camera, you extract some features. Or you have LiDAR scanner, you scan the environment, or RGBD camera that both can have the pixels and the distance of each pixel. Then you extract some features like the corner, edge, or some identical features that can be later also matched with the next frames during time. So this is called feature-based map that we have lots of different algorithms and techniques that works with this technique. Based on this technique, later on we will going to see. On the other hand, second type of the map that we can build and construct for our SLAM problem, we have occupancy grid mapping. That in occupancy grid mapping, the general idea is that we discretize the environment to the required resolution that we want. Then we say, okay, if robot is somewhere, with the existing sensors that we have, robot senses the distances, and we occupy the locations that the robot sees there are some objects over there. Exactly the environment that we are here, that if you look at the tiles and look at the objects, just we need to find out which one of the tiles are occupied and put some occupation there. But today we want to see in details how we can use the base filter and probability concept to fill this here. How certain we are that there is an obstacle here or not. It's not like 0 and 1 always. Because if we are that certain, the problem is like very okay and solved. But we have error, and based on the error, maybe one time your sensor model says that here there is obstacle, next time says there is no. Then what you want to do? You want to occupy it or not occupy it. So based on that, we want to bring the probability and the mass inside in order to be able to say how likely there is object over there. So if we want to construct 3D model of the occupancy grid mapping, at the beginning may look a little bit complex, but if we, in simplest form, if we just give the Z to the occupied location, that mostly whatever is in the environment somehow goes and has like a standing point. It's not on the air usually. Because of that, we just can simply use the 2D model and give the Z to have the 3D model. Like if you're detecting the wall, then you can extend it to three dimension. But on the other hand, realistic form is like there is a window. And of course, if you have a window, maybe the robot is drawn and can fly outside of the window. Then you need to have 3D model of the environment really based on the 3D construction that comes from, for example, laser scanner. Then what you have a cube that cube will be occupied or not occupied is the same concept. You just have a cube of these. Then each one of the elements that we have, we can say, okay, if it's occupied or not by scanning the environment and the sensor that we have, for example, RGBD or LiDAR scanner again. On the other hand, we can also have the point cloud. That next chapter, we also will see how we can deal with it. If you have visual information from environment, and at time t, your LiDAR scans the environment, then you have point cloud. It means that per each beam, like this is one beam that you're measuring. So you have millions of or hundreds, thousands of these points that gives you point of pixels in environment, then in 3D model. Then these point of pixels doesn't make sense for you, for your robot. You don't know, like, those are just pixels on the 3D construction. You don't know what is the wall, what is the chair. You just have a bunch of points. So these bunch of points at time t, added by time t plus 1, then another bunch of points come. And this is like series of millions of points that are coming. How we can bring them to the form of point clouds and how we can merge them together, also next chapter we will talk about. But today, our focus is based on the occupancy grid mapping, how we want to make a grid of environment and work on it. So far we know 3 different types of environments. The mapping for SLAM of the environment. Is it clear? Any question here? So for example, for feature mapping, how we can do that? Of course, we need to use different techniques of image processing, robot vision, and all the techniques that we can extract the features of the environment. There, what we can use, for example, we can use again the different kinds of sensors. The most common one is LiDAR scanner that in next slides we will see. So we say the basic idea is that we want to evenly spread field of binary random variables can show us which one of the grid cells is occupied or not occupied. So this is just general idea. And they are representing presence of obstacle in one location simply. They are basically non-parametric model we already have defined. And if you want to visually see what's happening, we want to say, okay, we have like probability of the being obstacle or not. I don't know how likely this is visible here. These are darker colors. These are white. These are black. So for darker colors, we can say, okay, we didn't see, we don't know, robot doesn't scan. But this area that is white, it means that we scanned, like I'm scanning. When I'm scanning, there is obstacle here. Of course, the line in middle, there is no obstacle. Because of my sensors, the measurement, the distance gives like 1 meter. So among this 1 meter, it's free. So I can use that technique to say these cells all are free. And this one is occupied. So when you do the scan, you can free up to obstacles, then put the obstacles over there. But the other parts, for example, in probability form, we say that those are free. And random variable, you know that if you talk about the tile, if we can have head and tail of the coin, then we can consider that is positive one, for example, negative one. And if you bring it to the probability form, then we have 50% of having the chance to that this coin is head or tail. So that we want to bring that form to the probability of each one of these grid cells to say it is occupied or free. Is it clear? Okay. One of the benefits that we have here, we don't need feature extraction, because feature extraction already is difficult, and we have some challenges and errors there. Later we will see. But of course, like we have different techniques. If you study different papers, recent papers, some of them are still based on the feature extraction, but some of them are based on the occupancy grid mapping. They are like competing against each other. So what are the important elements that we need to consider if we talk about occupancy grid mapping? Of course, the basic and the first one is the map size and the grid cell size. We need to think, and we need to kind of decide how discrete our environment map construction should be. On the other hand, we have the noise in perception. So this noise in perception should match this guy over here, usually, because if your noise is very big, then your grid cells is like the size can be effective on the amount of error based on the grid size that you have. We usually here, for simplicity in construction of the map, we say that already we are talking about the mapping part of SLAM, not localization. So we consider that localization already solved by, for example, Kalman filter, extended Kalman filter, whatever it is. Now we have the information, and based on that information, we want to focus to talk about the constructing the map as one of the important elements. So basically, we consider we have the output of, for example, EKF, UKF, or whatever the algorithm is as localization, and we're gonna construct our map. So other important parameter that we have is the perceptual ambiguity, that how frequently one location is looking like to another location in one environment. So if you have like corridor environment, that there are 10 corridors that they are exactly similar, and they look like just a corridor, empty corridor. So constructing map in such an environment, of course, has higher difficulties because they are very similar to each one. And even though if you have feature extraction of the environment, the other type, so the features are pretty similar, then that is the one of the important challenge in map construction. Like you have, for example, this environment, then robot is somewhere. Everywhere is looking like identical. There is no feature. So this is called well-known ambiguity of the environment. Then we need to rely on control commands, motion commands mostly, or odometry mostly, in order to be able to construct the map. And of course, we have more error, then there are more challenges over there. On the other hand, the cycles are also very difficult to talk about, as we know formally as loop closing problem, that like if your robot starts from here, moves, and then comes back from here, this is easier than if you make a loop. Why? Because after making a loop, we need to identify same location that we started. Robot starts from here, identifying the same location that robot starts, because we don't have any idea. It will take 1 minute or 1 hour of the rotating, then coming back. We can see it now. We can say, okay, that's easy. But in the algorithm, we have no idea. Maybe a robot starts from here, 5 hours later comes back, or 5 seconds later comes back. And maybe there can be very similar environments. Because of that, detecting the loop is harder than just going like and turning back and coming again. So we have the environment map of the occupancy grid mapping. You can see this kind of the environment. This comes from the book that we have. They've implemented the occupancy grid mapping and constructed the map, and you can see that occupied walls, the free environment, and the surrounding environment that we don't know what is there. Robot doesn't know what is there. So these are darker grayscale color. So for occupancy grid mapping, as you can see here, so we have here LiDAR scanner in the middle, and there are some obstacles, and that obstacles, like the LiDAR scanner scans the environment, and based on the distances that we have, you can see that we can put directly 0 and 1s on the grid map over here in this part, so that we have the simple map of the environment by saying that, okay, these are free, these are occupied ones. So by looking at this map, you can see that, okay, using occupancy grid mapping looks very interesting, because without doing any calculation, we can achieve this map construction just with having the range of the range and bearing of the sensor model that we have. So if our robot moves and continuously we can do that with applying the localization of the robot, then how accurate we are, we can construct our map over each one of the individual grid cells that we have. But what is the challenge? Why today course is coming up? Because when your robot moving based on this sensor, of course we have error, and these are moving, and we have error there. And again, as I mentioned to you, we don't know like how likely this should be occupied or how likely this, because we multiple times we will see that this is occupied or not occupied based on the error that we have on our measurement model. If you don't have error, then that's it. You have sensor, robot moves, you exactly say, okay, this cell is occupied or not occupied. How much time we moving, my sensor is accurate, I can say it is occupied or not. With 0, 1, I can work. And there is no need for probability model again. So now let's gradually start to dive in how we can bring mass insight in order to solve this problem. It will be a little bit complex in middle, but I will try to break it down as much as possible. As we already discussed, we can show the occupancy grid mapping like this. We can say our map M is equal to lots of grid cells, so that we can split our map to the I number of grid cells and indicate them with the index I, that we are going to show the binary occupancy value inside each one of these. That finally, if we consider 0 and 1s inside, whole of these, if whole map is occupied, should be sum of them represents our map. So, and the resolution, of course, is important. But if we want to bring it to the form of the occupancy probability, same as previous, we can write probability of MI. That says each one of these grid cells should come to the form of probability of how likely it is occupied or not. How much certain I am that this grid cell, for example, is occupied or not. So I have a question for you guys that states why only occupied. So we say this term over here refers to the probability that ice grid cell is occupied. So why only occupied? Simple question, yeah. What?
Can you
So here, the probability of mi, we say, shows how likely this grid cell is occupied, right? Now, we say why we say only it is occupied, why we are not saying, for example, it is not occupied. Yeah, because its probability is different. Because we are going to use it later in the math. Because probability of this grid cell, if we talk about occupation, occupied is 80%. The number is 80, but not occupied is 20%, right? So that if we want to calculate in probability form, then we should all the time talk everything about the occupied form. Okay? We can talk about not occupied, then we should say everything is not occupied over there. So this is the point that you should take into consideration first of all. Of course, that's simple and clear. So we say occupancy probability is the distribution of all states of the environment, and we can also represent that. Okay, if then we can write, if we, in previous slide we showed probability of mi, we can show the probability of m itself, whole map, is equal to probability of each one of the individual items, that here I is equal to 1 to n. So formulating whole constructions of the map. On the other hand, the golden standard that we have for occupancy grid mapping by given data can be calculated by posteriors over map, that we say the probability of m map given by observation 1 to t and the sequence of the all poses that robot has as x's. So what does it mean? It means that we want to construct the occupancy grid mapping today by observation and robot poses. So of course we used it already many times, but for localization, for example. We used it for EKF, UKF, different algorithms. But here today we have M here, not the pose. Or previously we had the X here, or the robot pose, or depending what we are going to do. But now we have the map that we want to have it as output by observation series and the robot poses that can come from any algorithm. So now we can also state the note that we don't have UT anymore here, control commands, because as I mentioned, we are not solving the localization problem. It already has been solved for us. We don't take anymore the control commands into consideration. Control command already has been used to have the observation that we have from the environment, and the control command already caused us the robot pose that we have. So it is second layer of algorithm that we are talking to. Is it clear? Any question? So as I mentioned, the common domain of occupancy grid mapping is 2D floor plan map, because it's simpler and we can simply construct 3D based on that, and 3D representation also can be done, but of course it increases the computational expenses. If your robot is not flying, usually we don't need 3D construction of the map if you want to solve this SLAM. But unless you have some specific task, for example, if your robot is like walking in the environment, is a humanoid robot or whatever it is, needs to, if a screwdriver, screw something, open something, work inside. One of the topics projects for Islam is that robots are going to work inside airplane. Inside airplane there are like, I think millions of meters of wires that takes years to people to wire them inside one airplane, and that's like brutal. And one of the projects that nowadays is one of hot topics is that robots can do the same job inside airplane. But of course, you cannot program it like exactly the position, everything. Still, SLAM should be worked there. maybe mapping part is not necessary. Constructing the map again is not necessary, but localization is very important there. So that there then you have 3D construction a map in detailed, where are the holes, where are the wires, and robot needs to do this. And there are like big projects ongoing on this, and there are many research papers that you can study. Also there we have optimization problem, which order, which one should be done first, and those topics are coming also to becomes more bold to be solved. Optimization techniques to have optimum solution for those. So for occupancy grid mapping, if you want to talk about decomposition, we can say, okay, probability of the map given by observation and robot poses can be written also as probability of each one of the grid cells given by the observation and poses by decomposition simply, but we are showing in a formal way. So instead of map now, constructing whole map, we want to consider constructing, talking about probability of each one of the grid cells that looks like this. We have each grid cell and probability of each one of them, and binary estimation problem can help us to solve this by bringing it to the probability, and recursively we can update each one of these by base filter, so that if you remember, we were talking about base filter that were bringing us to the point that we could calculate a belief, and that belief was in form of probability, but now we want to bring each one of these grid cells in a form that we can solve it with base filter in form of probability independently. So each one of them also can be called binary random variable. That I stated over there. As we discussed that observation, if you have the map like this, then at the beginning we have initial probability that how much is likely occupied. For example, 50% we don't know. If we don't know 50-50, 0.5. After observation comes, observation can tell us if we basically, for this chapter, let's consider like LiDAR scanner only, because other sensors is a little bit difficult to imagine and talk about. But anyway, whatever the sensor has, you are measuring the distance, and when your sensor robot from here measures the distance, the observation can say, okay, this cell is occupied or not occupied, and give us 0 and 1s as observation model. So as you can see, I stated some mass forms here. We can say this, for example, 1 here indicates probability of this grid cell is occupied 1. Generally, whole map can be written as probability of MI given by observation and series of robot poses. Then here, again, probability as 50%. But now we also talk about the point that I mentioned to you. We can say, for example, this grid cell, the probability of this grid cell, Mi, we can write it in this form. P of Mi is equal to 0. Or in another form of representation, we can say probability of not Mi is equal to 1, subtracted by probability of Mi. That is equal to 1. But basically, these are different presentation. So these 3 form of presentations, or 4 forms, well, we can show the three form of representation can be used in our calculations and math, but basically we will try to keep on the first 4. So especially with base filter and applying base filter calculation on the grid cell, we will need it. So now we want to see how we can bring the base filter to the gate. We have prior map. Then after prior map that we have measurement model. Measurement model, we already seen how we can represent it. But in simplest form, we can write probability of observation given by m and x. So far we know it. Now what we want to have, now we want to have posterior map after posterior one that gives us probability of each one of the grid cells that we want to take into the consideration of the observation. So here, measurement model says that observation given by map and x. Here, map given by observation and the poses. So they are swapped. So how we can achieve this, and at the same time how we can bring the Bayes filter inside. First of all, we need to have a look at the Bayes theorem again. That with Bayes theorem we said that we have probability of the A given by B is equal to this form of probability, that distribution of the B given by A times probability of A over probability of B. So this is like the simple and very famous Bayes theorem that we can apply on to bring this calculation to the posterior map. How that can be applied? Let's have a look. So we have the posterior that we says, okay, if you want to get the probability of MI given by observation and poses, that one over there, we can apply the Bayes theorem on this measurement model. Then we have this big term here. So by applying simply, of course, like the term looks a little bit big or complex, but if you look at this term over here, we just apply the Bayes theorem on this form to calculate the probability of measurement model. But the calculation of these in mass has some difficulties and challenges. That what we need to do, we need to apply the log odd form of representation to calculate this term over here. I'm not going to show details of the how this can, we can achieve it. There are lots of calculations. You can have a look if you want how we can apply this over there in the book. But let's see how we can bring it to log odd representation to be able to solve it. So first of all, what is the log odd representation? We say it is simplification of the calculation in mass that we use it in probability form, so that we can say each probability value is converted to corresponding log odd values of the internal storage for that value. Then we can efficiently update the probability value in fused operation. So first of all, we need to convert it to log odd forms. Then after doing the calculation of the probability, then bring it back. And we will see how we can do that. Just all those efforts is from prior observation to come to the construction of the map by applying the probability of Bayes filter. Also, the point is that we have instability of the numerical instability sometimes in the probability form, so that log odd can help us to avoid that. For example, in cases that the probabilities are near to 0 or 1. So one more point, that you can quickly integrate sensor data into the map based on using that form. So how it looks like, let's have a look. We say, first of all, we can present the odd of x as probability of x over probability of not x. So probability of one event is happening, probability of one event is not happening. So in other representation, other form of representation, as I mentioned, we can show it like probability of x over 1 subtracted by probability. It is the same meaning. On the other representation, we can say if it x happens, if it x not happening. So this is like this representation is also called odd ratio. After calculating the, after knowing that we have the odd ratio, now we want to bring that probability in form of the odd ratio. If you remember, we had the probability of the mi per each one of the grid cell, observation, and x's. So that representation of probability now wants to come to the form of odd. How that is happening? It is like looking like this. Then we can write probability of this happens or not happens. So probability of mi given by x and poses and not happening of these. Then it is looking like the form of odd representation, odd ratio of the each one of the grid cells. On the other hand, what we need to do now we need to apply the same Bayes theorem. So if we apply the Bayes theorem, what we will have for this part over here, we will have this term, and for this part over here, we will have this term. So we do the same job of the Bayes theorem in previous slide, but for happening one time here and not happening one time here. Again, I'm ignoring representation and proving how this is happening. You just can we just need to apply the Bayes theorem on this term over here. Then we will achieve finally this calculation with simplification, some lines of mass. Then for not happening, this one over there. After doing this, so what happened? We both applied the Bayes theorem, and we both also bring it to the odd ratio form. So now again, after putting these terms over here and doing simplification, what we can have this term over here, some mass again. I'm not going to also show exactly how that's happening with some, it is like some mass. You need to write it and simplify it. So the odd ratio of the probability of this grid cell is occupied over not occupied can be represented in this form. That says we applied the Bayes theorem on it. Now, is it clear generally what is happening here? So we applied two things, odd ratio, and second thing, Bayes theorem. First in this part, and second in this part. Then we calculated, then we simplified it. Clear? I just didn't show the just the calculation of how this is happening and simplification. Okay, we can do that, but I think not necessary. Now, this is in form of odd ratio. What about log odd? Now we need to bring it log odd as a solution to solve it. We just simply need to convert sums to the log odds. What does it mean? It means that, so now log odds can be written as log of the same equation here equal to adding by each one of these terms by log. Of course, bring it into the log odd form, first of all, not adding the log per each one of the probability forms, but also we need to convert it to the sum of the log odds over there. So that Generally, we say it is learning of ratio of probability of happening over not happening to term. But what we've done, for each one of the grid cells, instead of directly applying Bayes filter in order to calculate probability, we bring it to the log-odd form with some mass calculation to make it stable for calculate first. Second, easier or not easier, most importantly, less computationally and more stable solution for that in the SLAM problem. So now, if you want to bring it to the form of algorithm, you may say, okay, this looks like a big term, how we can implement it in code and how we can bring it to the algorithm form. First of all, we can say, let's have some definitions and simplification of writing. We can say, okay, log-odd form can be written as Lx equal to logarithm of probability of x is happening or not happening. It means that this Lx represents this term over here for me, okay? Then based on that, the updating rule of that big equation that I achieved in form of logarithmic presentation of each cell is occupied or not can be written with this form. How? We just replace this term here with the L of the x. Then we can write the L of the mi given by observation and x's is equal to this term over here, L of x. Instead of x, I put the term over here, added by so this L also represents the logarithm. Then the same term over here, so this one subtracted by the logarithm of mi. So generally, what I've done, this term represented by simplification of the Lx and written in this shorter form. So as stated in the many references for Islam, this term, first term, is called inverse of the sensor model. Why inverse of the sensor model? Because this comes from observation and robot pose. That based on that, we want to construct the map that we have. So based on that, we call it inverse model of the probability in log-odd forms. On the other hand, second part is the previous observation or posterior, that is recursive term and comes from the, if you have a look at the slides here, the posterior calculation that we calculated in this part, and this is the prior. And why prior? So if we want to generally, after applying Bayes filter, understanding what we are doing, actually, we have grid cell. Each one of the grid cells should update it by probability form, that we say, okay, if we want to apply the Bayes filter, actually, during the time, that time is increasing, each one comes in new probability. So that is one in posterior, one is prior. So the calculation of posterior prior should finally lead us to achieve the update of probability for that one in form of Bayes filter. So that this becomes how we can do that. Now, let's bring it more closer to programming and algorithmic form. What we do, so here, if you look at this term, I have more detailed explanation. So here you can see that we can say the L of the logarithm of the mi, each one of the grid cell, is the probability of the occupancy represented by log-odd ratio that already we've seen logarithm of the happening of the map that is occupied or not occupied, also can be written in this form, at the same form, so that we can we can consider this L of mi can be represented or also as L0, because also it is referring to prior of the map that we have. So why we didn't keep that LMI? So we could keep that too, but in the reference books usually they try to simplify to bring it to more closely to the algorithmic form. Because of that, instead of this term over here that represents the logarithmic of happening or not happening, we put L0 over there. I try to keep it steady with the resource book that we have. Now, what we can do, this term over here can be named as inverse of the sensor model, a function that is doing this term over here by given we send parameters the map, poses, and observation, added by this term over here by same definition can be written as L's of ti minus 1, and this term can be written as L0. So L0 is prior, this is posterior, then this is the inverse of the sensor model that gives us update of each one of the grid cells that we have. Now, based on this representation, now we can say finally we can bring everything back to the probability form, because those are in log odd forms, and if you want to do that, we can write probability of the mi given by observation xt is equal to this term over here that we have lt and I. So this calculation here that is in log odd form, after all those mass that we first bring it from probability to make it stable to log odd forms, after doing all calculation and bring it to the form of even algorithmic form, then we can return it by this term over here to the probability. 1 subtracted by 1 over 1 added by exponential of the logarithmic form of the t and I calculation. So now let's have a look how it looks like. We say algorithm of the occupancy grid map is given by this log odd form of inputs of the ti minus 1, xt, and observation. Observation robot pose and logarithmic probability of the previous one comes as input, and for each one of the cells, if mi is presented perceptual field of the observation t, if like it is in the observation field of the like robot sees that area, then we can calculate the form that all the calculations that we've done in log odd form. So this is same term that we calculated in previous slide. Otherwise, the previous one goes to new one. Whatever it was there as log odd form goes to new one. The minus t minus 1 comes to t1. Otherwise, in this case, otherwise if it's like the sensor is measuring this, or these grid cells will be in this line and will be calculated by log out, observation, and update based on base filter. But of course, so what about everything is clear except like inverse sensor model over here? I think I have it in next slide. Yeah. So how this inverse sensor model looks like? It looks like this. What does it mean? It means that we want to, from observation, bring everything into the consideration and calculation and return the L of if it's occupied or not. So we can say, first of all, the inputs are coming, which one of the grid cell we are talking about, the pose and observation. And if we consider x and y as center of mass of mi, what does it mean? For simplicity, we can say each one of the grid cell, we can calculate the center of mass of it, then calculate the range that we already done in mass, like the x and y, and calculate the bearing, of which, like this is the distance that I'm getting, distance of the obstacle or object that I have, then bearing, the angle that I have, range bearing calculations. Then calculating k, that this k is helping me to calculate these ifs. That these ifs represent different things. One is like, let me see. This is like whenever the cell is outside of the measurement range or behind the detected range. This if over here just says like the range is greater than minimum of this calculation that calculates the center of mass, and the measurement that we have says it is after that. And if it is like that, we return the L0. But if it's on the otherwise, if it's like not that one, like we can say if the observation T and K is among these values, it means that I'm calculating each one of the grid cells minimum and maximum. If it's after that, I say okay, use this term. If it's in middle, I say okay, return the occupied, because like the object is inside that grid cell. Otherwise, then it means that it is closer to me and put it as free. These three ifs represent that three conditions. Again, I'm measuring. That's obstacle there. So everything after that is free. First term. Then that obstacle itself, by calculation of the grid size, because that grid size is like over there under that. And that can be partially covered by the obstacle. That whenever it is, I'm calculating if it's inside that, with this if over here, if it's inside that grid cell, maybe it can be here and can be here if you consider it is grid cell. So if it's inside that area, I can say it is occupied. Otherwise, all the grid cells that are in the way to achieve that are free. We have some parameters. I stated for you that, for example, alpha is the thickness of the obstacle, beta is the width of the sensor beam. So width of the sensor beam is like for here is like very tiny, but it can be like big scan. So you can adjust the parameter of the scan size that you have. Because if you have bigger scan size and your grid cell is too small, or let's say whatever it is, the size of this one is, your grid size is very small, then this measurement is going to occupy many grid cells, not only one. With one beam, not anymore, we say calculation will be 0 for up to the obstacle, but also multiple of them will be occupied. And the L of occupied and free are amount of the evidence of the reading of the carrier that they are occupied or not, and this can come from the also the applying the sensor noise that we have. Also, how likely I can say my sensor observation model is like scanning accurately. Then you need to calculate it and bring it into the game. So now let's have a look what is happening if we bring if your robot is over here and there is an obstacle, and if you apply lockout, then your robot is here, then obstacle is here, then these grid cells will be free and not occupied. And if we want to show it in probability form, for example, to understand, so initially they are 0.5, then for example here these ones I didn't write again, they haven't changed, but here these will become 0, 0, 0, 1. So after like highly certainty of the update. But that one, what is happening, that one is like calculation and updating online. Robot is moving in the environment, measurement model comes with inverse sensor model, and we update all the time the probabilities over there with the base filter. Then this these are becoming with increasing gradually, so that I will show you soon an example. But before that, let's talk about the this technique over here. So we say, okay, let's say my scan, if consider the Telso again here, my scan, if it's not straight to the lines, parallel to the lines, and if it's like in angle, then how can I say which one of the grid cells are covered by my beam, by bearing that I have? So for example, you can see here that robot is there, and this beam that is scanning up to so far this obstacle over here is crossing some of these grid cells. How we can detect which one of these are covered with this beam? So we have different techniques for doing that. One of them is Bresenham's technique. That Bresenham's technique says, okay, you give the start and end of the line for me on the grid cells that you have, then it returns you which one of the grid cells are crossed by this line. A simple algorithm that gives you, like, you give start end, then in grid cells says which one of those grid cells are crossed by this line. Then you can know that, okay, these grid cells should be updated by inverse modulo by applying this one for which one of the eyes. This eye, so already we had this pose, already we have this observation, but you may ask, okay, where does the eye comes? This eye comes from here. So you give the algorithm, then say, okay, this should be updated. This next time the next range scan comes, you should say this should be updated. Clear? So you can have a look at this. I didn't show because it's like simple for loops and simple calculation of how this can achieve. But after doing that, after calculation of the occupancy probability grid mapping, so here we have architectural blueprint of the environment, and here we have occupancy grid mapping. By applying the same implementation and calculation from book, we can have a reference book that we have. We can have this one, that robot is moving, and you can see that these darker points are more likely to be obstacle and wall. These ones robot never seen, and these ones are more whiter. But we have some gray, more gray colors. Maybe it's not very visible here, but it's not like three colors. There are more grayish or more lighter colors that they are representing just probability. For example, the black one is 1, the white one is 0, and everything is scaling between 0 and 1 in order to say how likely the obstacle is over there. So all those efforts were for what? Because we have the error on the observation and the localization, and when your robot is moving in the environment, we wanted to update the occupancy of one grid cell so that we couldn't put simply 0, 1. We brought it into the form of base filter, and we saw that in probability form we have a problem that is not stable mathematically. To bring it more stable, we apply log-odd form. Then we adopted observation model, inverse observation model on that with visibly seeing what's happening. Then we achieved this map over here. So now we say if we don't have the robot pose, then what happens? If you don't have the robot pose, of course, after robot is moving in the environment, then the map can end up something like this. Why? Because if you don't have robot pose, or your robot pose has like some error, then even though we are using based on the base filter and probability form of the updating how likely this cell is occupied or free, but it is not accurate. Robot is moving, rotating, and one time constructing map like this, second time constructing map, second time then map looks like something very wrong. And this is really problem in Islam, and this is big big challenge over there. We will see how we can solve this in next week. We have iterative closest point, that there are different techniques and algorithms, how we can mathematically understand these constructions and maps, how we can match them together. There are different techniques. We will study together how that can work. So, I mean, not only we can use these techniques in 3D and visual SLAM based on 3D point cloud, but also after localization. You say, okay, I did my best with localization, I implemented, I tried a lot, implemented uncentered Kalman filter or extended Kalman, I learned the math, I did everything as much as I can, but it's still, and I did a lot to understand all this mapping, and I constructed the map finally, but output is like this. Oh, my professor is gonna be angry. Why the output is looking like this? It's not working. So, but after that, is still, if you have problem, this is common, we had more layer to also try to match this construction of the map together. So usually if you look at the commercial or big or recent algorithms of the SLAM, is like thousands of codes and many different layers in order to improve it. It's not like you can say, okay, I just implement EKF, then it works. Accuracy 90, 85%. No. After even doing that, even doing this construction, even not only considering, we did a strong job in first layer of like considering control commands, considering observation, bring everything to probability, bring everything to improvement. And after all those efforts, is still in second layer of mapping, is still we add another layer of base filter to still bring it into probability to improve it, but still you may end up here. Then you need to again add some more layers of algorithms to also match it and understand how exactly the map is and make it more accurate. Is there any question? Is it clear? Okay, so also we have like check a chicken egg problem already we stated. You know, right? Chicken is first or egg is first. On the other hand, we've talked about the observation models, and with the observation models, sometimes we also have multiple sensors. You have laser scanner and you have camera, or you have RGBD sensor. So how you can merge these together? So we call it a field of sensor fusion. Sensor fusion again is a big field of study. It's not like small at all, and there are, you can search about like sensor fusion algorithms in Google Scholar, and you see like after 2022 how many papers just published for this topic. So what does it mean? It means that you have two different kinds of sensor, how accurately understand this shaders over here to increase the accuracy of the detection. So this integration can come from not only visual information, can come from IMU2, for example. What is the tilt of your robot? What is the tilt of camera in order to scan the environment? So one example that we have here, you can see that we have the camera image here that is a stereo, that comes from the stereo camera. And here in the middle, we have the sparse display map. That this sparse display map is famous in computer vision and machine robot vision, that you can extract it by calculating the differences of two image frames. So you have two image frames from two independent cameras. Then the sparse display the disparity map. You can search. There are also, I think, libraries to do that. So you can have achieved this one. Then based on this this image and this sparse disparity map, how we can we do something for example, occupancy grid mapping localization? But we don't have LiDAR camera or something. Yeah, we can do. How we can do? Like you can merge these together in order to say which one of the cells most likely is occupied. So this is, for example, wall. So estimation of the wall over here. This also is possible. Of course, looks more complex, looks more harder, and it is. So when you have a stereo camera, and based on that stereo camera, you can bring it into the form of occupancy grid map. One of the techniques is like well-known technique that you have camera image, then you create the sparse disparity map, then construct this by merging them into the probability form. So, do we have any important point here? I've written that projecting disparity image into 2D plane and convolving the result with Gaussian over here, so that I forgot to mention that this is also coming from applying Gaussian on grid map, that we can do that too. So after discretizing the environment, not only we can apply the probability form, we can have apply Gaussian on the distribution that over here, that the probability that is increasing over here can be affected by the other cells. With today's course, we directly only talked about occupied or not occupied of one cell. We didn't say that, okay, if we can apply Gaussian model over here that not only change the probability over here, change the surrounding grid cells too. So that can be called as applying the Gaussian on the occupancy grid map too. We have many different techniques. Of course, we try to focus on some of them, important ones, but when you hear Gaussian, so just updating each one of grid cells by Gaussian probability, that more likely the probability that is in center highly will change. These were like lessly change. So now we have a question. You can think a little bit. We say, what if multiple sensors detect different characteristics? So you have a camera and you have a LiDAR, or RGBD sensor, or whatever, stereo camera. They are detecting different characteristics of the environment. Then what you do? We are talking about mapping and sensor fusion. Imagine you have robot, you have two cameras on, for example, Gogoro project. Yeah?
Same cameras?
No, different.
Okay, so I can check the covariance of the sensors and use the one with the smallest one. Like extended Kalman filter would do this with the
Yeah. Merging put both of them together, you mean? Or using one? Which one is more likely you want to use, or?
I mean, using the extended Kalman filter covariance matrix, the sensor will, let's say, it will say, okay, this one is more accurate, so it will
merge them together based on probability. Yeah, this can be one technique that came to your mind. So there are different ways to do that. Of course, one of the, like two of the most important ones I'm going to introduce here. So one is replacing the function of the inverse model, but what your friend mentioned. So by replacing the inverse model, it means that whatever comes from observation and my inverse model calculates it, I can merge it, for example, with extended Kalman filter in the probability form, which one is more likely, or update based on both of those. So that's one. Second one, the challenge that we have is detecting different types of obstacles on different sensors. That this makes what you said challenging. For example, so when your different sensors sees totally different things, then you don't have matching to which one is more likely to apply on it. So that's difficulties that we have over there. Also, like if you consider, so we have two sensors over here, right? So partially conflicted objects. So one of your sensors partially sees this one. The other one like sees all of this. But this sensor also sees another object, obstacle. And you don't know like this is like covered by that or not. So these are challenges that overlapped objects and partially seen visible objects are making challenge for us. So what do you think we can do with those cases? Of course, this depends on the error that we have and how maybe for example, you have two kinds of sensors. Sensor A has like 30% error, sensor B has 20% error. That this also makes inaccuracy over detection of this whole area and error over there. Then, so one of the ways is replacing inverse one. Second one is kind of constructing separate model for each sensor. So you can say I have two maps. One is coming from LiDAR that I have. One is coming from RGBD sensor that I have. Constructing totally separate maps. Finally, try to merge them together after construction. Because after construction, so you can see that, okay, your LiDAR says the map that I have is looking like maybe looks like this, and the other one looks like something similar but different, like this, like maybe this. So you have two maps based on the error, then try to merge them together, and we will see later on how, if you have those occupancy grid map output or mesh in 3D or 2D, we can merge them together, how we can do that. So any question? Is it clear here? So now we want to talk a little bit about a more interesting topic here based on the challenge that we've seen and the calculations that we've seen, how we can bring learning techniques into the game. We say if we can generate random triple of the poses, like the poses of xtk, and k is each one of the sensor type, the measurements also will come with the observation, and the map occupancy value with mk's for each one of the grid cells. Now you can think what we can do with these guys. So different sensors, like 3 different sensors, for example, LiDAR, camera, and an RGBD, for example. Then per each one we have the X, we have the observation, and we have also the map that comes from previous one. One is current and pose is current, and the map that is also the grid cell that I have already. Now think a little bit about how you would bring learning algorithms into the game here as a problem. So you can think, okay, these are input parameters for me, kind of. And based on input parameters, simply I can say, okay, let's say these input parameters, the poses that I have, the observations that I have for each one of the sensors, I can feed it to the neural network or deep learning techniques. Then this guy over there can give me the output as map, or output have pose of each one of the obstacle and pose of the pose of the robot, position of the obstacles and pose of the robot. If you have a robot, right, and robot has 2 types of sensor, and if you train a neural network based on thousands of times of trying, so the error on the observations is static in the sensor model that you have, right? So it's not going to change like too much, like your LiDAR has some predefined error. Your camera of the detection, the RGBD, has some error, right? Based on those pre-known almost error that is very hard for us to extract it if we just put like a camera at ground truth on the top and let the robot move in the environment too many times based on those observations and all the parameters as input, then your neural network will be learned based on true ground truth data. Then you can have probability of occupancy of each grid cell by that input. Is it clear, this one? Do you think, is there anybody who thinks that it won't work? So if you like, this can be your project too. It is a little bit big, I know, but can be. So it looks maybe complex, but then you don't have all those calculations and masses, you know. You just give these input parameters, and you want to throw out all those calculations that we've done in this class and put the observation and all inputs inside and finally construct the map. Okay, so I explained that we can have a function approximation that can receive the inputs as parameters. These inputs not only limited to, like, these poses still can come from Kalman filter, extended Kalman filter to make it accurate. Observation can be pure, but how much accurately we can give it to neural network, if it comes from the techniques that we've learned, of course, it will be able to do the job better. Here you can see the output of one learning technique with neural network. You can have a look at the book. Already this have been done on the SLAM problem by the also reference book that we have. So this is the blueprint of the environment. The robot moved in the environment, and you can see the output of the environment. But so here we have the point is that, of course, for neural network, you need to, for calculation backpropagation, it means that you push forward the data and backpropagate to update the weights of the neural network. You need to calculate the loss function. Loss function can be calculated by the differences of the map that you have and the blueprint directly here. It should have been here. So you need to have a reference point to say how accurately my prediction is, and what this is the prediction as output, and how accurate it really is. Then you can calculate the loss function and error, and based on that, based on different techniques, for example, stochastic gradient descent, SGD, update the weights of neural network, then it will be trained for you. And of course, its challenge is that training neural network in real environment is very hard, takes lots of time, and that's the reason that is not that easy to bring it to the game. So if you want to like really put the camera and train neural network in an online environment, it takes very, very long. That's the biggest problem. So here, now we have some questions that says, okay, can we make the learning independent of the robot pose or location? So here we have I said that the pose comes as input, right, to the learning, to the neural network. Can we remove it, do you think, as input, then do the same job? Now you should look at this problem as researcher and find an idea. Again, I have neural network, and I said that the pose and data and observation comes, then I have a map as output. The question is, can I remove this pose as input? How? The answer is yes. How?
You can guess it from the observation, so you don't need.
Yeah, very close. Yeah, this is one of the advanced techniques, and recently there are many studies on this topic that Hugo mentioned correctly. We say, okay, of course, if we have the poses, for example, output of Kalman filter or extended Kalman filter, that's great. Then we can have higher accuracy. But let's talk about if we have only observation as input, then you should understand this point very accurately. Then what we have, your robot doesn't know where is this. Then of course you cannot have the output as a map anymore, first of all. Then output is not complete map because your network doesn't know where it is. But what it can give you, the scanning surrounding obstacles and environment, and learn that my sensor, my scan says the obstacle is here. Is it really there? Scans and says which one of them is it really there, and actually learns the error model of the environment. And then the output is local map instead of global map, and says, okay, the locally wherever the robot is can more accurately gives you the map of that part only. Means that, so in first example, we say robot is here, robot moves in the environment, and the pose of xt is given at the first example. Then when you give the pose, then if there are some obstacles anywhere, then robot can give you the probability of each grid cell. So I'm not going to make a grid, and your neural network can give it even for this point, for each one of these, right? But when you remove the pose, then your neural network doesn't know where it is anymore. Only thing that you can get as output is only the range that robot can scan, the map of that area only. Did you get it? Then we don't have the map, just the map is local anymore with removing that pose. But still we can have it because this constructed map can be learned, and robot says, okay, I'm seeing that one, I'm seeing that one, I'm seeing that one, how accurately it is. When it comes here again, doesn't matter. So it can say the probability of, okay, what is this one, what is this area, then moves a little bit more, for example here, then what is this area. So you still can have it, but we have one more step again, how to merge these together. Outputs of each one again should be merged if you remove it. Now you can, as a researcher, think, okay, what we can feed more data based on problem that we know. If we want to solve loop closing problem, we can, instead of neural network, put deep learning here. We can apply some filters hierarchy here. For example, let's say I put unscented Kalman filter here. In observation model, I put another filter here to make it more accurate. I make it as deep learning, one specific characteristic with convolutional layers. Then the output, what should be like, let's say I want to, not only the map, I want to, for example, detect the velocity of the robot too. Then I can train my model to detect the velocity of robot too, and whatever the problem that I want. So then I become researcher. Then I become the who can face in with problem, then propose a solution to that problem. You are working in industry in real robotic problem, then you say, okay, I exactly know what's the SLAM problem. I know the parameters. I now know different tools. Then let's see how I can put them to finally achieve what I want. For example, let's say how we can merge IMU over here. In one of the latest research on Islam, we will discuss it. One of the input elements is IMU that goes for our measurement model and gives us more opportunity to calculate it. So what if I give IMU here? What does it mean? It means that I have one more element to velocity model. that I can say how fast my robot moved in the environment. Then I can construct map more accurate, right? If I can train my neural network. Then you see, you can, based on the tools that you can have, you can choose what should be input, what should be output, and middle what I need to do. Any question?
Can you expand that a bit?
This one? Yeah, here at the first stage, let's say robot has these poses as input. Okay, so one input says where the robot is exactly. If we know where the robot is, it means that robot, when moved in the environment, can update all grid cells. Don't consider these circles. So it means that since I know where it is, where the robot is, I can say that this obstacle is over here, right? Because I know the coordinate here. Clear? I know the coordinate. I can say the obstacle is over here based on this coordinate. My neural network output says the coordinate of this obstacle, the coordinate of the other obstacle. When I have the robot pose. When I don't have it, then I have no idea. I don't have no idea where it is, and I cannot. Your neural network cannot say where the coordinate of exact position of this robot is. This is relative. The coordinate will be relative to robot pose dynamically. That you can consider always 0, 0 if you remove the pose. If it's 0, 0, just says distance and angle is there. Range and bearing always. Then those range and bearing that is without x as output, then you should merge them together because you have a bunch of them. I feel you still didn't understand. So if I know coordinates, I know my position, my neural network can say exactly where the objects of class are, right? But if I don't know, I just can say the distance of these with me. I cannot say where they are in the class. Correct? I move, I don't know where they are. I just can say this is like 1 meter far from me. That's it. Then you need to again merge them together to say where they were and how they are related to each other. This is artificial neural network example by LiDAR scanner from the book that you have. It's applied for it's applied on the inverse measurement model. That you can see that what they've done. There is a LiDAR scanner. This is the robot, and these are the beams that has been presented. And you can see the constructing of this one look like that one, and this one look like that one. Here, the model haven't trained well. No. This one is like the noisy environment. You can see that the beams scanning like this and noisy, but here the robot is in the corridor, and based on the measurement that it has, output gives the output of each one, a probability for each one of the MIs, how likely there is obstacle or it is free. So why this is thick? Because the error is too big here. Sometimes it's scanned like this, that then it become thick wall over here. Otherwise, it should have been narrow. That shows the amount of error of training neural network for the measurement model based on the laser scan. So, is it clear? Question? So, what we studied today? We studied the map in measurement models first. Then we talked about the occupancy grid mapping, how we can formalize it, bring it into log forms in order to calculate our probability, and then bring it in the form of the algorithmic form. Then we talked about the sensor fusion concepts, general concepts. Of course, this has like 1 semester of course if we want to go into details, but general concepts are important. And finally, we talked about general idea of how we can bring and engage learning techniques into our only mapping part. But of course, that can be engaged into different parts of the SLAM too. We just only talked about how we can use it for occupancy grid mapping. So, any question? from today's course?